In the last lecture, we mentioned that ozone in the stratosphere, it absorbs sun's radiation. Hence, in the stratosphere, temperature increases with height. In the troposphere, temperature decreases as we go up. This is because in the troposphere, most of the radiation is absorbed at the surface, and in turn this absorbed heat is transferred to the troposphere by radiation and by evaporation and turbulent fluxes. So, in the troposphere, the highest temperatures are at the surface, and then it decreases with height up to tropopause. Above tropopause is the stratosphere, where ozone is there, and because ozone absorbs the ultraviolet radiation from the sun, it increases the temperature as we go higher. So, that is what makes Earth's atmosphere distinct. There are two layers: the troposphere, where the temperature decreases with height, and stratosphere, where temperature increases with height. Now, all of you have heard about ozone depletion, ozone hole. These words became popular 40 years ago, and a lot of people confuse the ozone depletion problem with global warming. These are two separate issues. Ozone depletion talks about reduction in the ozone in the stratosphere due to reaction with certain chemicals released by human beings. Where global warming is caused by carbon dioxide, which traps Earth's radiation. So, two are very distinct phenomena. One is concerned with solar radiation, another concerned with trapping of Earth's radiation. But of course, the two are related. They are related because ozone not only absorbs the ultraviolet radiation from the sun, it also absorbs radiation emitted by the Earth in the 9.6 micron band in the infrared. Okay? So, ozone is also a greenhouse gas, but it also plays a role in temperature increase in the stratosphere by absorbing sun's radiation. So, there is some connection, but the connection is not as simple as people might think. So, today we will talk about ozone depletion and its connection to climate change. This slide shows the ozone hole in Antarctica, which was discovered around 40 years ago. And it is called a hole because there is a region around Antarctica where the amount of ozone is much lower than the surrounding regions. It looks like a hole. And when it was first discovered, it caused major surprise because this was unexpected. Initially, no one knew why it happened, whether it was a natural phenomena or was it caused by human-induced causes. Once it was realized that this was caused by human-induced changes, a major effort was taken to control those substances which cause ozone depletion. And so that led to the well-known Montreal Protocol to limit the emission of those substances which deplete the ozone layer. Okay? Now, the ozone layer, the natural layer, is around the height of 20 to 25 kilometers in the Earth's stratosphere. And there is also ozone near the surface. It is much smaller than the ozone at the stratosphere, but this has an important impact on air pollution. This ozone near the surface causes serious problems for human beings and is related to air pollution. But this layer at the top in the stratosphere is very important for life on Earth because it removes the ultraviolet radiation from the sun, which otherwise would damage our DNA of all living beings. So without this layer, life cannot exist in the Earth's land surface. It can still exist deep in the ocean where ozone doesn't, where ultraviolet doesn't reach. But on the land surface, most living beings could not survive the damage created by ultraviolet radiation impinging on them. So this ozone layer is called the good ozone, which is critical for survival of life on the surface of the Earth. Okay? While the other ozone near the surface is the bad ozone, which causes a lot of problems for lungs and for human health. Now, because ozone absorbs ultraviolet radiation in the stratosphere, the temperature variation of the Earth has two layers, the layer called troposphere, where temperature decreases with height, and the layer called stratosphere, where it goes up, and the boundary is called tropopause, where the temperature pauses for a short distance. Okay? Now, this can be shown by climate models. In a climate model, if you remove ozone, you will get the green line here. That is, temperature will decrease from the surface all the way to the top of the atmosphere. Of course, the lapse rate will change between stratosphere and troposphere because in the troposphere, water vapor plays an important role. In the stratosphere, there is no water vapor, so it has a different lapse rate. But once you add ozone, you get the shape which we see here, and that shape depends upon whether CO2 is there or not. If the CO2 is not there, we will get a slightly colder Earth, okay, this red line. On the other hand, if you remove water vapor but not CO2, Earth will be even colder. Okay? But still the shapes will be similar. So what you see here is that as far as Earth's surface temperature is concerned, both CO2 and H2 are very important because they warm the Earth due to greenhouse effect. So greenhouse effect is something which is very important for life on Earth. Like ozone is important for life on Earth to prevent ultraviolet damage. Both CO2 and water vapor are important because their greenhouse effect keeps the temperature of the Earth above 10 degrees centigrade, which makes life evolve on Earth easily. Okay? So you might wonder, if CO2 and water vapor are so important for Earth's climate, why are we concerned about CO2 increase? Now, although CO2 is very important for life on Earth, too much of CO2 increases temperature so much that many life forms will have difficulty in surviving. So remember that when human beings were not there, the carbon dioxide level in the atmosphere was typically, for the last 3-4 million years, between 280 parts per million and 200 parts per million. It oscillated between these two. And so temperature of Earth was between 10 and 15 degrees centigrade, which was enough for life to survive on Earth for a long time. Now suddenly, in the last 100 years, by using fossil fuels, we have injected a huge amount of additional CO2, which was not a part of the natural carbon dioxide cycle, and hence increased the temperature by 1.5 degrees in the last 150 years, and is continuing to increase. And if this continues further, it will pose a lot of threat to many life forms on Earth, especially the mammals. Now, how much ozone is there? It is measured by an instrument called Dobson spectrometer. More than 100 years ago it was measured. And the amount of ozone that is measured by this spectrometer is called the Dobson unit. One Dobson unit is 0.01 millimeter of ozone. If all the ozone in the Earth is brought down to the surface, you will get a thickness of 0.01 millimeter if we have one Dobson unit of ozone. Typically we have 300 Dobson unit, so we typically have 3 millimeters of ozone if we take all the ozone in the earth and bring it to the surface. So that's a convenient way of understanding how much ozone is there. Okay. How was it measured? So an instrument called Dobson spectrometer was invented by Dobson, and he looked at the incoming ultraviolet radiation in two frequencies, one in which light UV light was not absorbed, and the other it was absorbed. So difference between these two wavelengths gave an idea of how much ozone was there. So this is a very standard method in today in many instruments. If you want to measure a particular gas in the atmosphere, you choose two wavelengths, one where it absorbs and a nearby wavelength where it doesn't absorb. Look at the difference. That difference tells you how much of that gas is there in the atmosphere. Now, why is ozone occurring in the atmosphere? Oxygen has always been there for a billion years or so, and this oxygen, when it encounters the ultraviolet radiation of the sun, which is very high energy, it splits oxygen into two parts, two atoms, O and O, and this oxygen atom interacts with oxygen molecule to give you O3. Okay? So this is the standard chemical reaction which is going on naturally for billions of years to create ozone, and this ozone layer was formed in the stratosphere a long time back when oxygen was there on the earth, and this ozone presence was necessary for life to exist on land. Before this ozone layer was there, life was still there, but it was in deep ocean. So the life from deep ocean could come over land and thrive only when the ozone layer was formed around the time when oxygen in the earth started increasing. Okay. So there are three regimes in the ultraviolet, and in one regime called UVA, ozone doesn't absorb much, it comes to the surface of the earth, and this ultraviolet radiation called UVA is very important for generating vitamin D in your body by absorption in the skin. So that's why doctors recommend that you go out in the sun for some time so that you produce natural vitamin D in your body. Okay. Now UVB is the slightly higher frequency radiation, which is partly absorbed by the ozone layer, but this frequency of ultraviolet is not good for human beings. If you expose yourself too long outside in the sun, you go sunbathing, for example, like many people do, then if you are fair skinned, this ultraviolet will go into your body and can cause skin cancer. Okay? So that's why people recommend that when you go out in the sun and you're a light skinned person, you should cover your skin with a suitable coating so that this ultraviolet B is not affecting your skin and your body. Finally, we have ultraviolet C, which is the one the ozone layer absorbs completely. So the good role played by ozone is by completely eliminating ultraviolet C, which is extremely damaging to our body. Okay? So ultraviolet C would make life unlivable on land, okay, where you are exposed to sun. Again, this graph shows in a little more detail the ultraviolet C, which is between 0.2 to 0.3 micron, ultraviolet B between 0.3 and 0.325, and ultraviolet A from 0.325 to 0.4. Okay? So UVA is okay and UVB is somewhat dangerous, but UVC is very, very deadly. Okay? Now here is a chemical reaction which produces ozone in the Earth's atmosphere. The photon from the sun in the ultraviolet splits, dissociates oxygen into two atoms, and these atoms in the presence of other molecules like nitrogen, oxygen and so on form ozone, and later on this ozone splits again to oxygen atom and oxygen molecule and produces oxygen molecule again, and this reaction goes on continuously generating ozone in the stratosphere. So here again the biological effect of ozone is mentioned. UVA was once thought to be harmless, but causes wrinkles, aging and skin damage, and new research shows it can cause skin cancer. UVB is harmful, causes sunburn, skin cancer and other disorders, and UVC is the most dangerous. Extremely harmful, damages DNA, but is absorbed by ozone. So ozone is very important in the stratosphere because it protects us. Now exposure to UV radiation causes skin cancer, sunburn, eye damage and cataracts, which is very common among old people. Okay? A 10% reduction in ozone layer causes a 25% increase in what is called non-melanoma skin cancer in temperate latitudes, not in the tropics but in high latitudes. By 2050, if you allow the ozone layer to deplete. I want to remind you, when there was no ozone layer in the stratosphere, life could only exist in the sea. So ozone layer in the stratosphere is very important. Okay? Now what is the typical column amount of ozone in Dobson units as given by NASA? You will see a very interesting difference. The highest amount of ozone exists in the higher latitudes, and ozone is somewhat smaller in the tropics. Okay? Because ozone is smaller in the tropics, we are getting more ultraviolet in our region, and that is why people who have lived in the tropics for long periods have a much darker skin, so that we are protected from the damage by ultraviolet. While people who evolved in higher latitudes, they have a lighter skin, because in the higher latitude there is more ozone, less ultraviolet radiation, and to produce enough vitamin D for their health, they need to have a lighter skin. But if the ozone layer starts depleting, the lighter skin will be harmful because it will cause skin cancer. Okay? So what you have to remember is that we need ultraviolet for good health, but too much ultraviolet in a certain frequency range is very bad for us. So this is a point it has to be remembered. Now here is a depiction of 30-year average column mean ozone in Dobson units, and you can see that the low amounts are there in the tropics around 260 Dobson units, while in the higher latitudes is more like 300. Okay? Except you can see a small region in the Antarctic where the ozone hole was discovered is quite low in the month of September, October, where the summer in the Antarctic occurs. Okay, remember that. Now let us compare the vertical profile of ozone in the polar region and tropical region. Is very different. The amount of ozone in the tropics is higher at a certain latitude. In the polar region is slightly lower, but take the integral, this will be more than this, because in this region you can see there is much more ozone in the polar region than in the tropics. So again, to remind you, there are two kinds of ozone. one ozone in the stratosphere, which is good for us because it removes harmful ultraviolet. There is another ozone near the surface generated by human activity, which is bad for our lungs and health. So, here is an indication of what effect surface ozone has on the respiratory system. Okay. Ozone can irritate the lungs, cause inflammation, and ozone can aggravate asthma, which many people have, and 10 to 20% of the summertime respiratory related problems are associated with ozone at the surface. The threat to stratospheric ozone is chlorine. Chlorine somehow reached the stratosphere, and chlorine is a highly reactive gas, all of you know that, and it started attacking the ozone layer in the 80s. Now, why did that happen? That is because freons were discovered by human beings in the 30s and were used in many applications like refrigerators, air conditioners and so on. And freon is a gas with a very long lifetime. It is was considered a very safe gas by engineers. It was used in refrigerators, air conditioners because it was non-flammable, non-toxic, non-reactive, odorless. So, it was considered very good to be used in domestic appliances, but because it had a long lifetime, it slowly diffused from the surface and went into the stratosphere. Once it went to the stratosphere, the ultraviolet C radiation from the sun split this chlorofluorocarbon and it released chlorine. Chlorofluorocarbon is a non-reactive substance, harmless, but once it gets split into chlorine, fluorine, they are highly reactive substances. So, they started removing ozone, and it was not realized for a long time until by accident the ozone hole was discovered in the 80s. Okay. This paper was published in 1974 when I was a student, and they showed how chlorine in the stratosphere can remove ozone. Okay. And when they first published the paper, people did not believe this result, and they thought that reduction of the ozone layer, reduction of the ozone in the stratosphere may be on account of natural causes, because remember that ozone will have a natural variation, because sun's output varies in a 11-year cycle. That can cause ozone variation, because ozone is generated by sun's ultraviolet radiation, and there could be other natural variation that can occur due to changes in temperature and circulation of the stratosphere. So, a lot of people said this is unnecessary fear, it will not be that serious. So, although steady decline in ozone layer in the stratosphere was predicted by many scientists, no one predicted a catastrophic decline in the ozone that led to the ozone hole in Antarctica. Okay. So, people started steadily decline, and so people were very casual. They thought we will see when it declines, we will take care of it. But by accident, it was discovered that it was declining catastrophically, okay, and forming a hole. This is a discovery by Farman, Gardner and Shanklin, published in Nature in 1985, almost 40 years ago. And you can see that the Dobson unit of ozone in the Antarctica, which was around 300, 325, started in 60s, suddenly started declining and reached 200, and it declined further. And this decline was related to the presence of chlorine in the stratosphere. Initially, when the results came, people did not believe it. They thought there was some problem with the instrument. Okay? For example, the satellite first discovered decline of ozone. But people didn't believe it. They thought there's some satellite problem. Then instruments shown here taken to Antarctica and measured Antarctica, they showed also decline. Then people realized something was not right. Okay. So in 1978 there was 300 Dobson unit of ozone in the stratosphere. By 84 it had gone to 180. So initial satellite data which showed low ozone was actually filtered out because they thought it was too low, something is wrong with the instrument. But when the ground-based instrument confirmed that ozone was indeed low, they realized it. Now, why was ozone so low in Antarctica but not in other parts of the world? Remember, the chlorofluorocarbon were released mainly in North America, okay, and in Europe. Now, the question is, when they released in North America and Europe, why did the ozone hole form first in Antarctica? Okay. Now, that is because of the peculiarity of Antarctica. Antarctica is a continent surrounded by a cold ocean, and there is an Antarctic vortex, which is strong wind which sort of maintains Antarctic air enclosed like a test tube. Okay. So, when the chlorofluorocarbon reached the Antarctic region from North America and Europe over a long period of time, they started splitting into chlorine, fluorine and carbon, and this chlorine, fluorine being a highly reactive chemicals, all of you know it, it started attacking the ozone layer in stratosphere, and because this layer was enclosed in this stratospheric vortex, which is called here containment vessel, okay, contained in that vessel had a rapid reduction in ozone. A reduction also seen in Arctic, but Arctic does not have such a enclosed vortex, so the reduction was not as dramatic. So the peculiar feature of Antarctica made the Antarctic ozone hole appear first in Antarctica. Okay. Now, this decline from the 60s to the 90s is shown in this data. Okay. And it also shows how it varied with latitude. Most of the decline occurred in the polar region and not in the tropics. Okay. So, how does ozone get depleted? So, first of all, the chlorofluorocarbon, which is a non-reactive substance, has to be dissociated by ultraviolet light into chlorine. This chlorine reacts with ozone to produce chlorine oxide, which interacts with oxygen molecule to produce oxygen atom, and then two chlorine oxide molecules join together and finally form chlorine ozone. This shows how there is a cycle. Chlorine is dissociated to form chlorine atom, which reacts with the ozone and the oxygen, and finally it forms chlorine again and comes back. So, chlorine is able to repeatedly come back and attack the ozone. So, this something was not understood in the first papers published in 1974, that chlorine will get a chance to attack the ozone many times, not just once. Now, this is shown by this thing, and a single chlorine atom can destroy as many as 100,000 ozone molecules during their residence in the stratosphere. This is the remarkable result due to certain heterogeneous reaction which take place in the Antarctic region. This was not realized in the first paper published in 1974. They had predicted a slow depletion of the ozone layer, but it occurred much faster because of this unusual fact that chlorine was recreated after every reaction, and it came back to attack the ozone molecule again and again, almost 100,000 times. So when this ozone hole was discovered, there was immediate realization that this is a serious matter because it causes cancer. So the Montreal Protocol on substances that deplete the ozone layer was finally agreed on 16 September 1987 in the International Civil Aviation Organization in Montreal. Okay. This is a landmark agreement globally, because this is the first time there was a global agreement to control the production of certain substance which affects the Earth's chemical composition. Okay? So before that, there was no real global agreement on anything, and each country did what it wanted. But once we realized that the Earth's atmosphere is one, and whether chlorofluorocarbon is released in Chicago or in Cancun or in London or in Paris or in Delhi, it ultimately reaches the Antarctic region and start depleting ozone. So once it was realized that Earth's atmosphere is a single unit, then it became important for the human being to realize that we need to control the release of such substances, and an international agreement is required to monitor the release of such substances. So at the time when Montreal Protocol was signed, we didn't fully understand the complex reactions which cause the depletion of the ozone layer. But fortunately, the Montreal Protocol was a very flexible instrument which could alter the protocol every few years as more scientific data came. Okay? This was a very important feature. It was not a one-time agreement, the agreement which was looked at again and again every few years, and as it became clear that the destruction of the ozone was going on more and more rapidly, more and more stringent protocols were imposed. Okay? So only after the initial framework was negotiated that the science became clearer, and early conclusions were really underestimates. Okay? So all the 142 developing countries which initially were exempted from this because they are not creating much of these chlorofluorocarbons, they were finally able to meet the 100% phase out for the chlorofluorocarbon and halogens and other ozone depleting substances by 2010. So you remember from 1987 to 2010 is a period of 23 years. So the Montreal Protocol was continuously modified until all the countries in the world were able to stop the release of these chemicals. Okay? It was not a single protocol, a protocol was modified continuously. Now, why did this chemical reaction become more active was understood only much later, because they found out there were certain kind of unique clouds called the polar stratospheric clouds, which trigger a heterogeneous reaction which was not considered by earlier models. Earlier models consider only homogeneous reaction between gas molecules, but when there is a surface like ice there which produces or gives a lot of surface area. Suppose ice is a porous substance, it gives a lot of surface area for a chlorine and ozone molecules to react rapidly. This is called catalyst in chemistry. So the clouds played a role of catalyst and accelerated the destruction of ozone, and this was discovered much later, well after the Montreal Protocol was signed. But fortunately, the protocol was flexible and they could do it. Just one word about the discovery of chlorofluorocarbons by Thomas Midgley. It was considered in 1930s as a great achievement because this chemical could be used in refrigerators, air conditioners and many other household devices, and it was considered very safe because it was not toxic, it was not reactive, did not have any odor, it was not flammable. So many things which sulfur dioxide, methane did not have. Okay? So earlier refrigerators used methane and sulfur dioxide, which are very toxic substances. So Thomas Midgley was given many awards for discovering this harmless chemical, but later we realized this chemical was not that harmless. So this shows that we need to continuously do research to understand the role of various chemicals we are now inventing through our ingenuity. But if these chemicals remain in the atmosphere a long time, they can do a lot of damage. Okay? This is what we learned from the ozone hole story. So I will continue the lecture in the next class when I look at more about the relationship between ozone and Earth's climate.